Hello, Rob.
Oh, hello.
How are you?
Feeling much better.
Only little, huh? Still going on.
I've got a slight cough, but I'm medically cleared. I've got a letter from the board, the IDPH, and it's just they say that you'll have a lingering cough for a week or two.
Okay.
And the big thing is they want to make sure is you don't run a fever because I guess they consider that to be the dangerous part. So,
So that's good. Yeah. So how was the experience?
um, I did not have as rough of a time. My wife is having a real rough time with it. My kids didn't really have that rough of a time. Um, I've got I don't get sick very often. So my immune system is pretty robust.
Okay. Okay. And how is she feeling now? Like your wife?
She is still, for her, it's the coughing is just really bad. And um, she's just feeling miserable. But she's got a pulse oximeter to keep track of her blood oxygen level, and as long as that doesn't drop and get to a risky level, she's okay.
Okay. Okay. Yeah. Yeah.
Are you at the university by any chance, Rob?
Yes,
Oh, did you already test negative?
they CDC requirements. You have to. They have a timeline, and I'm beyond the timeline of being considered infection risk.
Oh, I see.
Okay. Good. Good. That's good.
So you have a battle inside of your body.
I think that was over with before. I think right now it's just the aftermath.
Aftermath of battle. So both sides are counting how many dead bodies they have.
So, oh, the lack of smell. I can taste, but my sense of smell is still kind of off.
Ah,
I heard.
this is what Jordan was also pointing out, right? Jordan's wife,
Yes, yes.
taste and smell.
Yeah, I heard my mother had all the symptoms,
Some
like
people have the
like months.
symptoms, but they're not severe. Some people think it's a sinus infection.
Mm-hmm.
But lack of smell and taste at the same time, and muscle pain. No, that is not sinus infection.
No, that's usually, and that's the only reason that I realized that it probably wasn't. Is about the same time my wife stopped being able to smell, I stopped being able to smell.
Okay. Yeah. 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 Good. Yeah. As far as everything is good. Yeah. I hope it was not my course.
No, no, um, we live in an area that people just flaunt the guidelines and they don't listen to any of the recommendations. And and that was more than likely when I talked to the lady from the health department. Um, it was she goes, we just assume that at places like Walmart and all that there are multiple undiagnosed infected people there.
Yeah. 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 Okay. Where are others in the? We're missing people, right? 1, 2, 3, 4. 4 of us. Okay. Let's. Since it's the last lecture, I cannot probably move it to another class, right? So let's begin. Ah, Moses is here. Yeah. Hey, Moses. So a few things about the course. Let's see. So homework 10 has been cancelled officially. Like what it means is that homework 10 problems have been moved to final exam. So homework 10 is not due, but that's just changing the name of something. So everything stays the same. Final exam. Two problems are from homework 10. So there will be 4 problems overall. So 4 problems. 2 of them, 2 from homework 10, which is available as of now. One will be on Drude model. So one on Drude model, which I'm just not getting the time to finalize it, but it's mostly ready. And the other one, I intend to make it on plasma model. These are dielectric models we are studying. So it should be, especially the first Drude model, it should be pretty much out of the lecture. So you should be able to look into the appropriate lecture and get it done. This one will be simpler, but this might be out of the lecture. So that might be the only challenge you have. And these two, the first 2 problems from the homework, I intend to cover that today in the lecture. So most of today's lecture you should be able to use for the 2 problems that has been moved from homework 10 into the midterm or into the final exam. This is all due on December 9, Wednesday at 4:45 p.m. But since you guys have an exam that is due, another course that is due on Tuesday, I'm fine with before Friday. But I would also say that it's probably not too much, so finish it off. So and enjoy your holidays instead of keeping on working on these problems. Okay. I also wanted to say there's a course evaluation that's available on D2L. And I'll encourage you guys to take that. It should take about 5 to 10 minutes. That is it. Anything else that you think I should address? Okay. So today we want to talk about conservation of energy, and mostly all these dielectric models have this naively, when you look at it, it seems like they violate causality, especially the plasma model. And I sort of hinted on it in the last lecture, but let me do that in a little more detail. So we do know that the dielectric responses are defined in the following form. We have the displacement current. All these are position dependent, but we are interested in the frequency dependence here. So that's epsilon omega. Let's keep it isotropic. It's making it simple. In general, this can be a dyadic. A X component can polarize the material in the Y direction. That sort of stuff. And the time dependence, just for your information, this should read minus infinity, and since it is causal, this should be t prime epsilon t minus t prime and E of P prime. So it's a response in the sense you give this and you get the left-hand side. So that's but we want to be in the frequency space because it's algebraic. And magnetic field, similarly, is mu of omega times h of omega. For most of today's discussion, let's set mu is equal to mu naught. So there's no magnetic material, it's all electric material. Again, that is just to simplify the analysis because we are talking about a sensitive, a very delicate relation. So it's good to avoid complicated stuff. Okay. We also said there is a conservation equation, conservation of reads. And let's derive that. So let's start. Just accept that. So let's derive that. Let's remind ourselves of the Maxwell's equation. So that is del. Erase this later on. So this is what is this? Rho del dot B is equal to 0. And we have del cross E plus, let me write it as minus, is equal to 0, and del cross H, oops, H minus is equal to J, which is so H. And the way you would derive your conservation equation is start from power, right? I'll write that here. Let me move this. Still getting used to. Yeah, I'll erase this part, but still. Okay. So we can start with J started with E. Is this readable, by the way? Am I writing too small?
Yeah, this actually looks better than last time.
Better than last time.
Yes.
I mean, the department?
Yes.
Yes.
Oh, I see. So that's what Jordan always says. It is better this way here. I think it's because I zoom it in. Okay. Okay, J. J, substitute this. Let me write it here. Sorry. I need more space. This is let's del crossed with H minus E by dt. So the same derivation we did some time ago, and that started with E. And let me say that plus, I can always add this quantity which is 0. That's just a trick. It's a 0, I can, since it's a scalar, I want to multiply scalar, so I multiply it with H dot, right? So it's perfectly fine because it's 0. Collect the two terms together. These two terms, what's wrong here? Something is wrong. Something is wrong. Oh, no, probably not. Yeah, okay. Yeah, so we have minus, let me write this term here as E dotted with E by T. Then I have minus H dotted with E by dt. So that's two outer relations. And we have minus del cross E dotted with H and plus del cross H dotted with E. One can show that this is actually a divergence of a cross product. So this is the same as minus E dotted with and this is minus of divergence of E crossed with H. You recognize this as S, and this is written as a total derivative, but this is a crucial step now. Notice what happens if you're in vacuum, right? Only if you're in vacuum, we are going to argue that this is not completely always easy to do. So if you're in vacuum, you can say this is equal to minus epsilon naught, and then you have E dotted with E by dt, and this is mu naught H dotted with H by dt, and notice if this is a constant with respect to time, this can come out of the derivative, then this is nothing but x times dx by dt is like, it's like the kinetic energy, right? If you have a velocity times the acceleration, that's nothing but kinetic energy like relation. So remember d by dt of v square is basically v dotted with dv by dt. And I need a factor of 2 there. So if you use that relation, am I still in visible region? Yes, so I can write one more step, I suppose. So then you write, oh, this is nothing but d by dt, the total derivative of half epsilon naught e squared plus half mu naught times h squared. It's E crossed H, which is basically S. But we would like to criticize this relation if we are not in vacuum. If we are inside a material, this need not work. And that's what we want to be a little, we want to see this a little more delicately, that's all. Okay. So let me write this equation up there in the form that we know. So that's minus or plus actually E dotted with, while you guys are writing that, I'll just rewrite that equation there. It's plus H and this is plus S plus J dotted with E is equal to 0. Okay. Any questions at this stage? Okay, so I want to go up again. Okay. Right. That's our relation. And we're asking, is it possible to write du by dt or not? So that's the connection. But so that is one thing we can do. And let's say that we are in a medium that is constant, right? Epsilon is constant. So epsilon is greater than epsilon naught, but it is frequency independent of frequency. That's called a non-dispersive medium. Right? Often when we are doing experiments, we say that the refractive index is independent of color. Right? That's not very always true. Sometimes when you use glasses, sometimes you see colored things on the corners. That means that different colors behave differently in a lens. But let's assume that the whole, make it simple, the whole universe is filled with an epsilon. It is not vacuum, but it's a material, but it is non-dispersive. Every color behaves the same. In that case, I can still do the same thing. I can bring out that epsilon, right? This time it is not epsilon naught. I can still do that epsilon trick, and I will get d if, right? So let me say, specify that if epsilon is independent of time, right? This time it's time. time, and in the frequency space, it will be independent of frequency. In that case, we can say that you have d by dt u plus j dotted with e 0, and by this we mean non-dispersive. And our conclusion here will be that all the materials are dispersive, so we have to take care of that. And when we take care of that, certain things happen, which in fact is good. And u here, just for our purposes, that's half e dotted with e plus half h dotted with e. And s is equal to e crossed with h. We want to talk about causality here, how things go faster than light, and then we have to ask, what do we mean by something going faster than light? And you might have often heard that something going, it is okay for things to go faster than light as far as you don't communicate, carry information with it or carry energy with it. Information has to do with energy. So we want to define that a little more precisely. So let's, for that purpose, we want to define the rate at which velocity, energy is being transferred. So we want to talk about if there is a wave packet, so how does the energy move? So what we want to do is let's multiply this by r. So remember that this is non-dispersive. We'll come back here and do this for dispersive case. But assuming it is non-dispersive, multiply this with an r and integrate with respect to in a small region of volume. So think of a wave. So this is so think of a wave packet. So there's a pulse of light. So in quantum mechanics, we call it a wave packet, but more realistically, in optics, you would call it a pulse of light. Right? So there's a pulse of light, and it's moving to the right. It doesn't necessarily mean that every point in here is moving with the same velocity. This pulse can change its shape as it is moving. So all that is possible. And to analyze that, what we do is we integrate. So what this is in a region, let's say I'm showing only the x direction. So, so very descriptively, have my volume enclosing this pulse. So I consider a volume V that encloses this pulse, and then I integrate this equation on that volume V. So, but before that, I multiply an R. So I multiply by a vector R, position vector R. I multiply by U, and then I do an integral with respect to dr, dq bar on this volume V. And there is a time derivative that can come out of this integral, this time derivative. So I'm basically integrating over this volume V and working with this equation. Do the same thing in here, plus integrate with respect to R, but before integrating, multiply by a position vector R. So clearly, this is a vector. That's a divergence is a scalar, so that's a vector, but the gradient acts only on the S. And plus the same thing, and it's on a volume V, and this is J dotted with E, and dqr is equal to 0 on the volume V. Let us say the volume V in which we are integrating doesn't have any charges inside it. Right? We can always
You still have to multiply the third term by r, right?
Yes, the third term has to be multiplied by R. You're correct. Thank you. So that's R. And okay. So let's consider a situation where there are no charges inside this volume. Like this is just going through a medium, and I can always have a situation where there is no charges, and I want to analyze that particular situation just for simplicity again. So let's say J inside of this volume is equal to 0. which basically means charge and current, no charges and currents. That basically kills that term, right? And when I integrate over the volume, that's gone. Okay. That is this term here. What I'm going to do is integrate by parts and see what I can do with it. So notice that divergence of S times R is equal to the divergence of S alone times R, plus I can act on the other piece, but when I act on the other piece, I have to still dot it with S, and that gives me a dyadic, right? That's a unit dyadic. Circle quantity is a unit dyadic. We have used that plenty of times. So that's just unit dyadic, that's S then. So this is divergence of S times R plus S itself. This is what appears in this integral. So R can be kept anywhere I want, but these are not operators. I can move things around. So this quantity is what appears in this integral. So if I were to integrate this, I will get what is there in here, right? Okay, so when I integrate this quantity, this is integral of d cubed. Oh, can you guys read it? Probably not. I move the. Integrate this. Basically, I want to evaluate that. So that's total divergence of a quantity is equal to this is what we would like to have. So it's times R, and this is E cube R times S. This is a divergence. Using divergence theorem, this will contribute only on the surface. If it contributes only on the surface, and if there are no fields on the surface, this is zero. So that's where this pulse idea of a pulse comes in. A pulse by construction is that most of the energy is confined inside the volume. There's nothing on the surface. Right? When I showed this blip there, that main idea is that electric field is zero if you take this volume far enough. So there's nothing on the surface. It's all confined inside of the volume V. If you want all the energies inside our universe, there is nothing on the surface. That's one way of looking at it. But we want to think of this as an actual pulse, a realistic pulse inside our lab. And this is confined in space. And if I take my volume V larger than that confinement, I will get nothing on the surface. So this is zero. So this term goes to zero. That means to say that this integral here is nothing but negative of the integral of ds. So overall, what we have is, as an equation, time derivative of an integral e cube r of r vector r of u. This term gives you a negative sign, so I'll take it onto the right-hand side, is actually equal to the integral of the pointing vector, which is E crossed with H, but let me write it as S. Think of the interpretation here. This is the flux, right? Rate at which flux of energy is moving. And this is the rate of change of, what would you think of, like suppose I were to give you this expression, what does something ring or something like this, you've seen it before in some other context. What does this look like? What would you define this? How about that? If I were to give you the option to define this integral.
Power times distance.
Yeah, that's okay. Not power, that's energy, right? Energy times distance. Energy.
But there's also time integral, right?
Yeah, but okay, maybe I should ask, what is this quantity? What would you say is this quantity? Where else do you see such a thing? In, let's say, Newtonian physics?
Are you referring to like a force over a distance?
Be louder, I think, whoever is speaking.
Were you just referring to something like force over a distance?
Oh, there is a lag here. George, is it? I think it's you who's speaking, right?
Maybe I might be lagging.
Yeah, but now it's okay. Yeah, go ahead.
Are you just referring to something like force over a distance?
Force over distance. No, that's energy. Suppose there is a position. If you integrate over something, average over position is what? What do you average over position on? Center of mass? Right? How do you define center of mass? What you would do is G cube R, right? Position, and this will be your charge, mass density, right? The density and density will cancel. Mass times distance defines your center of mass, correct? Is that clear? Right? So it is like saying weighted mass. You weight your position with respect to mass. Right? This is a distribution. If you average all the positions, you will get the average, but this is a weighted average, right? That's what center of mass is. It's a weighted average. Agreed? Is that clear? With that analogy, what would you say is here? This one. So this point here would be mass times the center of mass. So this is mass, total mass, times the position of the center of mass. What would I define here? This is energy density, so that's center of energy. So if you have a lot of, so in your room, there is an energy distribution. In one corner of the room, there is more energy, and in another corner of the room, there is less energy. You would like to define something called a center of mass of energy. It's not center of mass, center of energy, basically. Right? You don't even say mass, center of energy. So this is center of energy if I divide it out by the mass. Right? So I would like to divide it out by mass then. So, energy. So I do this. So what's the total energy? I would do d cube R times U. Since this is all since the total energy is conserved, I don't have to worry about the time. Right? We are talking about the total energy everywhere. When I integrate it over all space, then that's a total energy that's not expected to change. So we are saying total energy inside of this volume V is not changing as it is moving. So that is the position, a position of the center of energy. So I have to do the same thing on the right hand side. E Q R U. Let me define this to be the center of energy. And so what we have here is d by dt of, this is an average quantity. So this is best written like this. Right? So it's center of energy. And that's defined as integral d cube R S of d cube R times U. Good. That's nothing but velocity. So we have the velocity of a point inside a pulse which is moving, right? It's like saying if there is a mass distribution that is not rigid and you're moving it, then you would talk about the movement of the center of mass. Right? When the whole solar system is moving around the galaxy, you don't want the details. You say, I'm going to talk about the center of mass of the solar system. So similarly, instead of talking about this pulse, we are going to talk about a point in the pulse where the energy is concentrated, and that's the velocity of that point. And that's given in terms of integral of S and integral of U in that volume V. So we have a reasonable idea of okay, what the velocity is. So that velocity, we would like it not to go faster than speed of light. If it goes faster than speed of light, that's not causal. That's what we are going to recognize. Okay, so with that, let's see what happens for an actual. So we said it is non-dispersive, everything constant. So let's evaluate what this is. So VE, and let's forget the, let's make it, all the considerations we will make is that electric field is perpendicular to the magnetic field. Think of a monochromatic wave. That's just for simplicity, but in principle, you can make it more elaborate. Also, in a monochromatic wave, the energy in the electric field is exactly the same as the energy in the magnetic field. So that relation is also satisfied. So that's again, for simplicity, that just allows us to make this integrals very easy to do. And let's say that this is all constant within that region, or make an approximation that that's what it is. So just to capture the estimate of how much it is. So then the volume would not be there. So S is, let's just talk about the magnitude. So this is the magnitude of the velocity. This would be E times H, magnitude of the electric field, magnitude of the magnetic field, and total energy in U is half of that and half of that, so that makes it epsilon E squared. Remember, we are not in vacuum, we are in a non-dispersive medium where everything is uniform. One of the E cancels out, so we have 1 over epsilon, H over E. That's H over E will be epsilon over mu, right? So that's epsilon over mu. And that's 1 over epsilon mu square root. Which is, of course, makes sense a lot, because if I were to have been vacuum, that's basically replaced by epsilon naught mu naught. That makes perfect sense. Let's define refractive index as C over VE. That's equal to 1 over epsilon naught mu naught and epsilon mu naught. So and if we require that the velocity V of this center of energy has to be less than the speed of light, that means the refractive index has to be greater than 1. But all this is for non-dispersive media. Now let's see what happens if you bring in the color dependence or the frequency dependence into this. So let's go back and see what would happen. And there is a concern here right away is that, remember, we already had a model where is my, where should I write this? I think I can write somewhere here. So this is epsilon over epsilon naught was equal to 1 minus I gamma omega minus omega squared. So that's a very elaborate model we constructed. Let's make it simple. Gamma is 0, omega is 0. So that's epsilon over epsilon naught is 1 minus omega p square minus omega square. So there are always, if the frequency is large enough, these two can be neglected. Or you can say, I have a model in which gamma is 0 and omega naught is 0. And this immediately becomes less than 1. If this is less than 1, this will be less than 1 for a non-magnetic material. So, so that's surely not a convenient thing. So immediately we say that, oh, it's at least in this way of doing it, we are seeing that the refractive index is larger than 1. Not okay. But we will, how we are going to fix this is that we are going to say there is no such thing as non-dispersive medium. The material has to be dispersive. And when we take care of the dispersion, then this is going to get fixed. This is suddenly going to get less than 1. So what? So that's it. That's the argument of Brilliant, and we'll go through that now. Okay. Okay. So going back, we have. Let's consider the piece inside the, let's say there was an electric energy part to it. Let's keep this like this. Started with energy was built out of this, and now we are saying we are in dispersive media, right? There is time dependence in the epsilon knots, but this is all in time. In time, this is all real, so I can say this is star. It doesn't matter because the electric field is a real quantity, so that's a star quantity here. And now let me go to the Fourier space. So this is the omega over 2 pi e raised to minus I omega t times electric field. Now this is omega, right? So remember, if some quantity in the complex space, this is the same as E of minus omega. I think we have done that in other context. In a frequency space, the complex conjugate is nothing but minus omega. But for now, let me just say this is E of omega times star. And this should also be star, so this is plus. So it becomes a plus. So that's because it is a star dotted with time derivative of another integral. This time I had to use another frequency, that's d omega prime, because otherwise there will be a because this is dummy variable. That's minus I omega prime t times d of omega now. But d of omega is algebraic, right? So I can write, so d of omega, remember, is equal to epsilon omega times e of omega. So use that. So epsilon omega times e of omega prime. Okay, so that's an expression there. And when I take the time derivative, if I take the time derivative, this will bring down a minus I omega. That is the only place where it hits that. Right. But this was a real quantity. I could have put the star on this side. This is a correct expression, but this is also equal to this. Who says? That was just for convenience. I chose that star. So this time I will write the same expression again with this. So I'll average this as half of this term plus the second term, which I will write using this replacement. So this is plus half of d omega over 2 pi. And let me, since this is an integral, it doesn't matter what I call it, but I'll, just as a trick, this time I'll call it d omega prime. So this is minus I omega prime t. And this is E of omega prime. And should I do this? Yeah, let it stay as it is. Yeah. So this is omega prime and derivative of minus infinity to plus infinity d omega over 2 pi e raised to, now it's complex conjugate, so it is I omega t, and this is epsilon omega star and e of omega star.
So why did the
Take
sign?
the derivative and add them together. So this is the same as 1 by 2 minus infinity to plus infinity d omega over 2 pi omega prime over 2 pi. When I take the derivative, it will bring down a minus I omega prime. After that, I can combine the exponentials because that can go through. So that's e exponential of I omega minus omega prime. And that's there in both the terms, right? This is I omega minus omega prime, I omega minus omega prime. E omega star is there in both, right? So that's also common. So this is E omega star dotted with E of omega prime. All that is common. And whatever is remaining now has to be shared between the two. This one, when it takes the derivative, it brings down a minus I omega prime. And this one gives me an I omega. So let me put that together. So this is I omega times epsilon omega star. And from the top, I have minus I omega prime times epsilon omega prime. Okay. We have done sufficient simplifications, and since again we are bringing out the main point out, let's make one more simplification. This is a little strong assumption, but it's okay. And that is that, let's say this is real. It sounds innocent, okay, that a dielectric material should have a real frequency dependence. That's not very realistic, because what it is saying is that there is no dissipation in the system, there is no energy lost in the system. But we know that if you were more realistic, there is no such material. There are no materials where you cannot lose energy. You will always lose energy. In fact, it comes out to be as a theorem that you have to dissipate energy if you want to interact with electromagnetic waves. But to avoid those arguments, you can always say, just to justify what we are doing, you can say that that's so tiny, the dissipation is only necessary. It doesn't mean that it can always be small enough that it is negligible in our consideration. So that's one way you can avoid that. But you can generalize this, but again, this is for simplicity. For simplicity, if we were to do this, so that makes this real. So you can actually write this as epsilon omega itself. Okay, so that's going to be our assumption. Now notice, our goal was to remove this derivative. When it is non-dispersive, I could remove this derivative all the way out, and then I could do some analysis for the velocity of the center of energy. But I have taken off that derivative. I actually evaluated that. So I want to put it back. Now I want to put back that derivative so that I can define energy density. this time a more complicated version. So if I were to put in a derivative, that's equivalent to having I omega minus omega prime, because this will bring down that, right? So let me introduce a time derivative, and I want to fix that, like somehow undo that too. So this is not the same as the first expression. So I have to undo it. So this is e raised to I omega minus omega prime times t electric field square, let's say, or this is a different frequency, omega and omega prime. But what does this derivative do? Let me write that whole expression also. So this is omega, and we have already assumed that this is real. So that plays an important role, that's being, or that's a significant simplification that you should be careful about when you doing it in some other context. But this is not equal, right? These two lines are not equal. I introduced a time derivative. But what did I add? When I do a time derivative, I bring out this exponential I omega minus omega prime. I bring down that factor in. I just have to divide that out. That's I omega minus omega prime. So when I take the time derivative, it hits only on this term. It brings down that I omega minus omega prime. That kills that denominator. And that's the same as the numerator. So that's, these two are identical expressions now. And then I know that this is the expression that looks very convoluted, or so that's your U, right? Energy. In the Fourier space, that's a Fourier transform of this energy density, if you want. So that's your U, U of t. In a dispersive media, that's how it looks like. We can actually make this better. This quantity here, that is some function minus another function evaluated at another point. So this is like, recall f of x minus f of x prime divided by x minus x prime, right? And if I were to make this small enough, x minus x prime was small enough, that's like derivative, right? So again, we are talking about a pulse, remember. If the pulse had all the frequencies within a small band, it was not completely a unique frequency, or it did not have a lot of dispersion in it, but all the frequencies were close to each other. Again, just to bring out the argument, we can make it in general. So if they were all close, this can be thought of as a derivative. So you would say U of t actually can be defined as 1 by 2 omega over 2 pi omega prime over 2 pi. So there's a lot of convolution in the frequency dependencies. It's okay. And electric field. So this is nothing but E squared, complex conjugate of this. If we are saying that omega is the same as omega prime, very close to that. So this is nothing but E squared in the frequency space. And this I cancels out, and this is nothing but derivative with respect to frequency of frequency multiplied by epsilon, which is a frequency dependent quantity. And that's the key. So this is what Brilliant pointed out. So what is he saying? Let's make it simpler. Summarize this in a.
So you still have the t though.
Yes.
On the exponential.
Tell that again.
You should still have the t on the exponential, right?
Oh, t, yes. Is that what he said?
Yeah.
Yeah, so I missed writing that. Sorry. Yeah, that is a t. Yeah. Okay. So the key point is, if I were to put it if you didn't have so much time to derive this, and if you're defining this, in a non-dispersive medium, in the frequency space, energy density is equal to half epsilon E square plus half mu h square. Right? And when we write this, we never bother about, oh, is this frequency dependent? Is this time dependent? So these are all frequency dependent quantity, but this is typically we say this in non-dispersive medium. But if you're working in non-dispersive medium, then you have the risk that things can go faster than speed of light. So what is it in dispersive media? That's equal to, not this is equal to 1/2 times, instead of epsilon, you have to take a derivative with frequency. This is a function of omega. Notice that if this was frequency independent, right? If this was frequency independent, this only derivative acts only on omega, and that's epsilon itself. So the expression is more complicated. And you can generalize this for magnetic material also, even though we did not consider that. So this is omega times mu times h squared. Notice that if epsilon omega is epsilon itself, right? There is no frequency dependence. Then you have d by d omega of omega times epsilon is nothing but, it acts on the first one, that's epsilon, plus the second one, if it is 0, if it is non-dispersive, this is 0. So you get back your non-dispersive solution using this expression. So energy, all the while I was doing this in the course, that was a cheat, right? It doesn't work all the time. This is the correct definition of energy. And now let's see, okay, if that is the case, now let's see what happens to our velocity of center of energy, right? It should save us, this is expected to, or Brillon's claim is that this will save us from violating causality or things going faster than speed of light. So let's go back and do our same analysis, VE. And this is what appears in your homework, right? In some form, I am asking something about this. Right? So velocity of the center of mass, right? There's a magnitude. So that's equal to integral of S over E. It's, again, let's say it is all perpendicular and it's all confined in a region. This is nothing but, what was it? E times H. Yeah, E or S, very broadly speaking, S over U, right? But both has electric field in it, so this is nothing but E times H over, let's say, again, energy is equally distributed in magnetic and electric, so that's epsilon E squared. This time not epsilon E squared, right? Be careful. The new definition comes in. So this is equal to 1/2. So let's say this is non-magnetic. So this is d by d omega, omega epsilon times E squared. And there is a part in the magnetic also, but that magnetic material we are saying this is all 1. So that's just simply 1/2. And since the energy is the same, we are saying that's epsilon E squared. That's again a simplification. Okay. Replace your H also. So this becomes epsilon over epsilon naught. Sorry, epsilon over mu, right? Epsilon over mu times E. Divide out by E's completely. So the definition for your velocity becomes epsilon over we are having non-magnetic material, that's mu naught divided by, let me write this in the front, so that's 1 by 2 epsilon. I can put the 2 on the numerator, so that's 2 in the numerator. That's epsilon plus derivative of omega times epsilon. Now let's see how this comes out for the model we are considering. Okay. While you guys ponder that, let me erase this board. Oh, I should give a hint for the exam. The exam question, so this is what I derived. So the claim in the exam is that this can be written in another form, like it can be written as a square root inverse of, so that the exam you have to show that this is actually equal to d by d omega times epsilon over epsilon naught, and inverse of this. So basically, take the derivative of this, show that derivative of this, start from the right or left and get to the other. It's pretty much algebra you have to do. So that's what the exam problem is. Okay, so let's come back to verifying that this really saves us. So let me write that expression down again. So velocity of center of energy is, let's do this by divided by c also, right? Velocity VE over c is equal to, c is epsilon over epsilon naught over mu naught. So this is epsilon naught mu naught, and there's a factor of 2 epsilon over mu naught, because in the material that's what it is, square root also, right? And divided by epsilon plus derivative with respect to omega of omega times epsilon. Let me put in cancel out the mu naught, bring the epsilon down. So this is the same as, so divide out by epsilon. So this is the same as 2 times epsilon over epsilon naught. Remember, epsilon is frequency dependent. So divided by epsilon over epsilon naught plus derivative so that we can use our model. Okay, we were testing it with our model. The worst model was a plasma model, and where this was having most problem was this was 1 minus omega p square over omega square. Right away, this is 1 minus, so this is negative. How can this be? How is this allowed? That's what our question was. So let's substitute in this. Let's take a derivative. First of all, we need a derivative here, right? So let me do derivative of epsilon over epsilon naught. Sorry, d by d omega. This goes away, 1 doesn't contribute. This is minus, but then when I take the derivative with omega square, there is a minus 2 that comes in. So it is 2 times omega p square over omega cube. But let me multiply that omega in there. So this is omega square. So that means what will happen here? So this will be equal to, I have 2 times square root of 1 minus omega p square over omega naught square. And divided by, this is 1 minus omega p square over omega naught square. When I take the derivative with omega, that is, I'm left out with omega minus epsilon over epsilon naught, but what is that is nothing but the same quantity. plus 1 minus omega p square over omega
I have
naught.
one question.
Yes, please.
So how did we go from omega p square over omega square to omega p square over omega naught square?
Where did I do that? Oh, no, this is omega square, sorry. That was a mistake. Any other confusion?
No, that's all for now.
Yeah, sorry about that. I started writing, but carried away. Yeah. So again, substituting the same thing here. So maybe let me do this in 2 steps, just in case there's a confusion with that. Like this is the important piece, right? Whether the derivation comes in or not, this is what you should take home. So this is epsilon over epsilon naught. This can hit on the first omega. That just gives me epsilon over epsilon naught. Or I can hit derivative of omega with epsilon over epsilon naught. Right? That's what this is. This is 2 times this. So I have to put in 2 times that. So this is 2 times 1 minus omega p square over omega square divided by 2 times 1 minus omega p square over omega naught square plus omega times this. We just now evaluated.
I think it's still omega square.
Oh, come on. Yeah, sorry. Thank you. This is. Thank you. Okay. And you clearly see that the denominator terms cancel out. Crucial part. 2 cancels out. So what we have here is velocity of the center of energy is equal to 1 minus omega p square over omega square root. And this is always less than 1. So again, energy is not half epsilon naught E square or half epsilon E square. It is actually half derivative omega times epsilon. So that's the correct definition of energy. It's just convenient to use this instead of this in most places, especially in introductory physics. That's too much of a clutter that could be confusing. So that's convenient to use, but this is the correct definition of, and in a material, you have to bring in the frequency dependence, very crucial. And then that's good. This was done in 1914 by Brilliant. Remember, relativity was there in 1905, so almost about 9 years, this was an open problem. So it was not at all convenient. And this is very nicely done. Brilliant wrote a book on this wave propagation and group velocity. It's a nice thing to go through sometime. You don't have to do it now, but it's a good reference to keep in mind. And sometime when you're doing research or something, you might need that. That's all. That's the end of the semester as far as I'm concerned, and I'm 7 minutes early. At least in the last class, I did not go over. Right? I was afraid I had to cover all this, so I came prepared. Otherwise, I just come here and think.
So are we not going to do
Good.
methods of
So-
images?
Oh, there's again a lag. Could you repeat that again?
So what I said was, are we not going to cover methods of images?
That's in your homework.
There is?
Everything doesn't have to be covered, right? I think Jordan was asking me that, or Jordan was not asking. No, the point was that method of images has. Did I not? Okay, hold on. Yeah, I did not cover method of images. Yeah, sorry.
I think,
Oh, it is there in the homework of the other lecture. Yeah, sorry. Avinash, you're not there in that.
oh, that's fine, yeah.
Yeah. So, Yeah, you have to miss something. Yeah.
That's fine.
If I teach everything, then it becomes harder also. So excuse me on that. Yeah, but it is a good point to cover. As a course, one should have it. I take liberties of, like this is, for example, not often covered, but I feel this is also important, but I'm not saying that this is more important than method of images. Somewhere you have to sacrifice. So if you don't mind, yeah, and I don't think I'll be covering that next semester either. The next semester we'll get into magnetism. So, but you guys know method of images because you've seen it in another homework, except Rob has not seen it. Rob and so at least you're not ignorant about it. So,
Yeah, Rob will see it next
so
time.
yeah. So,
Well, Avinash would have saw it in your 320 class, right?
I think so, yes.
could you repeat that? This is really lagging at the end.
I was saying Avinash must have seen it in your 320 class, which is the lectures we use to learn it for this course or for the other course as well.
Yeah, I think I missed it, but I think you were trying to say that Avinash has seen it in the undergraduate lecture, probably.
Yes.
Yeah. But yeah, it's part of the syllabus. Yeah. But yeah, I'll assume that you guys won't complain. If you guys low grades, just complain that this was not covered. I spent all the semester working on this, and you didn't ask that. Right. So that's a loophole.
Then they'll just look to math methods where I missed points on the method of images portion and realize that it was covered, just not in the course I complained about.
But yeah, that's all I have. Thanks for listening. But you have one more semester, I suppose. Most probably, most of you would be there one more semester. It's not the end. Next semester, we will start with magnetism and then get into relativity and then get into radiation, which is basically scattering and radiation, how antennas work, basic form, not that you'll be able to build these modern antennas, but the basic function of an antenna, very primitive, simple version of it, which has it is like doing Newtonian physics, right? You cannot make bridges using the Newtonian physics. It's covered in physics courses, but it has all the essential things in it, pretty much like that. Yeah. And the relativity part should be nice. Even though you might have taken relativity in the classical mechanics course, this will address the electromagnetic feature of it. And it was really relativity that led to, it was electromagnetism that led to relativity, almost immediate. I mean, I think, and it took Einstein to realize that the physics of that was realized only by Einstein. Everyone had those equations forever, for almost 10, 15 years. It was it's good to appreciate that hopefully comes out. But again, thanks for listening anyway. You guys were nice. You kept me, at least I think more credit goes to Jordan. He kept it alive, I think. All of you guys contributed, but it seemed like Jordan was the one behind the force. Right?
Just have a big mouth.
I think you can allow him to have that. Oh, I should also mention, I wanted to, I think it has never happened in my courses that anyone got 100% until the end. And this time, I think Luke has 100% in this course. He has not missed a single point. I don't know whether he knows that or not. So
That's great.
That's pretty
Wow.
impressive. So I thought I should point that out. And Rob also has a high score in the class, and most of you are doing well. So it's probably going to be easy to grade. So I plan to give, make sure, I don't want to tell this because then you guys stop working, right? So I plan to give A's and A minuses. That's what I might do. So, okay. Probably all above 90 might be A. So Luke might lose there. I cannot help Luke, like your. So whether it's 100 or 90, all of them get a and then 80 to 90 A minus. So hopefully this helps you guys feel better, but still submit. I need the submissions, but don't stress. Okay. Hopefully that's relief. I don't know. Sometimes you're aiming for more, or sometimes you're aiming for less. I've come across situations where I've given a grade and I didn't expect this, and I was spending all the time trying to help, and oh, this is more than what I wanted. So let me know if there is a dissatisfaction or something, but at least I can justify it. It's easier to justify because it's, I think I've been lenient. Okay. So hopefully that takes away some amount of stress in the last weeks. But still, again, do submit. It doesn't mean that you can stop submissions. That will change your grades. Yeah. That's all. Thank you.
Well, thank you.
Oh,
Thank you.
exact 15. Yeah. We should end the course at the right time.
Alrighty.
Everybody take care.
Or at least I'm officially done. Yeah.
You
You
too.
too. Thank you.
Thank you. Can't wait to see you guys
Oh,
next semester.
Nice.
Yeah.
Yeah. Yeah. Have they
I think I lost you guys. I didn't hear you guys. Yeah. I think there's a lag here. Was it the same way when I was talking for you guys?
I
don't
can hear you
notice any
fine.
lag.
It seems like
Yeah.
things went wrong. Huh.
Sounded like Jordan was going to say something and then he left.
My dogs are barking.
Okay.
Wow, is this my home internet or is it the Zoom behaving bad?
It's a good question. I know they have been having bandwidth issues.
Well, the question that I was going to ask was pertaining to if they've decided how next semester will work exactly.
Yes, it is decided. It's going to be exactly like this. Exactly like this. All the teachers were given the option of whether it is hybrid or online. And whatever shows up on the course, if it is hybrid, it's going to be like this. At least I will be conducting it exactly like this. You guys can suggest if you want me to teach from home or in the department. I like the department. There is more board space probably there, but probably I should zoom inside in the department also. That might solve the problem. Right?
That would probably be good.
Yeah.
There's still some recording because it should be, if the internet is better, it should have better quality if the camera is good. Because even here, you can tell that the quality is not what the camera probably should be able to give you. So I'm not sure
I see.
if it's a setting somewhere or, you know, if it's Zoom, I'm not sure.
So your point is that relative to March, this quality has decreased.
I don't know if you were just always zoomed in last semester, but the quality it feels like it's not as good as it was, especially in the classroom. And you notice when you make the uploads that it's in 360p, which is basically like 1970s quality television. Oh,
Okay, I think I missed some of it.
I was just saying that 360p is the quality that it's uploaded in. So I'm assuming that's the quality that it's also recorded in. Now I don't. Yeah.
Now there is a difference here. One difference is that no, actually last semester also I did the same. I record it on the cloud. And since they have to communicate using the internet, based on the quality of the internet, they decide the resolution. Now, it is possible that last semester, it is not my settings, I did not change anything. They were more liberal with it. They used to allow high definition recording probably. That's a possibility. And I do remember what you're saying, that when I was uploading it, it actually tells me the resolution, and it used to be different. I agree to that. But I did not change any setting to the best of my knowledge.
But I'm saying even with Zoom, even now, the quality is not like an HD image that we see. It's
Yeah.
Yeah, it's like a standard definition, like
Okay.
480.
I hear you. Yeah.
I don't know why. I guess that could just be Zoom. They could just limit how much bandwidth you get per room, or I'm not sure.
Actually, this winter,
that's what you
I'm
get.
thinking, yeah,
I was gonna say that's what you get if the, what do you call that, stocks are increasing.
I did not understand. Avinash, ask
So
again.
what I said is that's what you get if the stocks for Zoom company is increasing. They just don't care about the customers. When they were starting, they wanted to give like really good customer service. They had really high-end service. Now everybody's using this. Their stocks are rising, and they're like, "Hey, we have enough customers," so they don't care about us.
Hopefully that's not the case, but could be, I guess.
That's
One
how things usually work.
is, yeah, it's possible. I don't know. Yeah, usually. But I wanted to get one feedback from you guys. I'm thinking of maybe getting this. I looked up in the market, and there are these document cameras, which points on the table instead of the board. And I can work on the paper. And if there is enough space, I can work on one paper, keep it on a corner, work on second paper, keep it on a corner, and it will be like a board itself. I want to experiment that. So I'm planning to do that in this winter. I might check that out.
I think
that might be better, less space. So hopefully it might have better resolution. And let's see if I succeed in that or not. So that might be the only change that will happen between today and next semester.
Isn't that already available in the room that you teach in?
There is a document. There is a document camera. Yes, that's correct. That's correct. And why am I not using that? Let me see. Yes. Yeah, that's because, okay, that will require me to share the screen. So what will happen is that will come on my computer, and then to share it with you guys, I will have to share the screen on the Zoom. And my experience has been that sharing screen is significantly slower and more data, at least when I look at the file, than the normal video. I don't know why.
Gotcha.
A share screen is significant. Like for example, the other day, yeah, it was Jordan, you were actually talking to me on Wednesday. Typically this file size is about 300 MB for 1 hour video. Just because we shared the screen on that day, that became 1.1 GB. That's about 4 times. at least 3 times, not 4.
So that has
I
to
don't know
do
why
with,
that.
that has to do with the quality that your camera is recording in is far less than the resolution of your screen itself. So
Maybe,
you're,
maybe.
Yeah.
Yeah. So the point I was trying to make is that if I use a document camera, that will be much bigger files I'll be dealing with, and the information content will be much bigger. So it's much easier to just use a normal camera and use this video in it. The quality might reduce, but I think we don't need such high quality as far as you can resolve what I'm writing. That's good enough, I suppose. We need to make the file sizes small also, because just for being safe on the bandwidth.
I honestly didn't have any
About-
trouble all semester.
Go ahead.
I honestly didn't have any trouble all semester following you on the board in the
So-
lectures, even with the quality it was. I mean,
That's good to know, because that's what most probably will happen. But I want to check it out, just experiment as to if it is possible or not. It's also expensive. The whole point is experimenting. This involves buying something, and if I don't like it, I lose that money. So that's something that might stop me from doing it too. So this one will be from my pocket. Like last semester, it was nice. Department actually paid for this camera. So that was nice, but department won't do that all the time, right? So you cannot keep experimenting. So yeah, we'll see.
I think this is a workable solution.
for sure.
Yeah.
Being zoomed in a little bit more helps. Yeah, the resolution on the uploads is not super high, but it's still workable.
Yeah. Yeah, that's the main idea. I think we're not like surely it's not high-end professional classroom here.
Yeah.
It does the job. That's the main thing. Main thing is
For the most part, yeah. On the uploads, there are a couple of just a couple of instances where it's like I can't quite resolve what you wrote. And usually it's okay because you're saying what you're writing as you're writing it. But if I were to just like, try to go through quickly and pause the video at the whole board, there would be like there would be instances where I can't read what it is.
For sure.
That's the only thing.
I should zoom in. I think I should start making sure that I always zoom in. That should be the way to go.
I think one of the solutions is you write bigger writings, like you have bigger letters and numbers.
Yeah, I can try that, but this is something I have tried for quite some time and I failed. What I do typically in an auditorium is that I don't use the small chalk. I use the big chalk. So that forces you to write big. So I can try to bring a pen which will force me to write big kind of.
What I will say as well is when you have done lectures in the math meetings on Thursday from time to time, and you use the chalkboard, using the same setup you have, it
Yeah.
was much easier to read on the chalkboard than it is on the whiteboard. And it was the same.
Oh, really?
Same exact setup.
I see. And you have seen those videos you're saying?
Yes. Mm-hmm.
Okay. Interesting. Okay. I can do that, but the only catch in that is that then students cannot come to the classroom.
I guess it depends on how many
Allows-
students you have per. how many
Yeah, that
students
room
per
allows only
semester?
one actually, one person.
Okay. Yeah.
So that's the conference room. You remember, right? Classical mechanics class was held there.
Yeah.
So I don't think then students won't be able to come in. But board, okay, blackboard is a good solution. Okay, let's see. Maybe I can think of a room which has a board. Engineering department surely has one. Let's see. Let me think about it. Yeah. That's a good point that you're making. So when it is white on black is significantly better.
And it could just be that when you write with a piece of chalk, it's less runny.
Or it's thicker. Or maybe just change the pen then, right? I should use a pen which will force me to write bigger or thicker.
Yeah, I guess you'd have to find a big dry erase. I'm sure they exist.
Yeah. Okay. Okay, good feedback. Yeah. Okay. Okay, thanks again for you guys were pretty, I say, engaging. I think that's the word. In this context, yeah. Thank you for that. Yeah.
Thank you.
Thanks for giving engaging lectures.
Okay. Thank you. Yeah.
Yes, it's nice. Not all professors went out of their way as much to record lectures, and having a recording in this sort of time and circumstances is very beneficial, especially if somebody gets sick or if things like, I mean, can you imagine how far behind I would have been if the lectures were not recorded? I mean, I don't know that I would have been able to keep up at all. But because the lectures were recorded, you know, at 1 a.m. when I'm done with everything, I could watch a lecture and get caught up, you know, which I would not have been able to do in the standard. So that is appreciated from my end, because my goal is to learn as a graduate student, and I was able to do that regardless of the circumstances. So I do appreciate the recording. I would not have survived without them, for sure.
Well, I'm just happy to be here.
Yeah, we're happy to have you, Avinash.
True. Sorry, I'm missing half of what you guys are saying because of the connection. There's a lag. Yeah. So if I'm not responding, I'm not just there.
Okay. Well, I have a lot of work to do.
Yeah, me too.
I'm gonna try to focus my energy and stay awake, drink some coffee. Thank you again. Bye-bye.
Yeah,
See
thank
you
you.
guys.
I'll see you guys
Yeah.
next semester.
Bye, guys.
Bye.
Bye, Michael.